right. So thanks everyone for coming. I didn't expect like the audience to be so big. So thanks to Sean for organizing this. So today I'm going to talk about this learning from close ones, a simulation study. And from title, you kind of have a feeling of what it's about. But before that, I would like to open up by like an anecdote. Right, so, but this could be controversial. So if you find this controversial, please like take this to be a hypothetical scenario. Just don't take me to be an unreasonable or crazy person. So, right. So I guess that most of you have heard of the rumor of our former president's dissertation. Okay, I'm going to touch this. Well, as I say, I'm not going to say anything like overly controversial, just slightly. Okay, so for those who are unfamiliar with this topic, well, some people claim that our former president didn't actually complete her PhD degree. She didn't submit her thesis according to what I found, and then one of her examiners were not an academic. Well, there are all kinds of things. I don't know. I really don't know. But if you check out all the evidence, you're like, yeah, maybe they could be right. They could be right, but it's also possible that this is all because of like some careless administrative staff. It's well possible. Okay, we can all imagine that. Right. So, but this is not the anecdote itself. And the anecdote was that when the rumor spreads like in our country around, its peak was around 2020 or before that. And by the time I was at university, I was studying there, and then so I heard about all these things. So there was a person who claimed that she speaks for the school and say that she did receive her PhD degree, and then so she claimed herself to be the head of the research institute or something. Okay, and then I read it from news, and it's cool. Okay, so. Actually met her in an occasion. So it was a reception held by the philosophy department. I saw her, interact with her, and actually called Zollman. I said, hey, Zollman, she's here. Do you want to like chat with her or something? So I actually had a conversation with her, and we even hang out together. We went to like a small party or something. Given my intuition, or given my judgment, I feel like she might not be a very, very reliable person. I was like, yeah, maybe sometimes she could be interpreting the evidence in a slightly distorted way. That's only my conjecture. That's only my feeling. Right. So this is what I learned. Right. Anyway, and then I got back here in Taiwan. I talked with like some people about this, and there were some people who I find brilliant and smart and good at interpreting evidence who believed in this conspiracy theory. Well, I call it conspiracy theory because still, you can see that my position is that I'm not 100% confident in this, but I was like, yeah, she probably did it. There were some mistakes, it's fine. But I know that there are some professors or doctors who have been awarded with like many things who believe that she didn't really get the degree. And I was like, yeah, this is strange. So on one side, you have a fairly unreliable, according to my personal opinion, you have a fairly unreliable person who's on your side, who's like, whose position, who believes in something you agree with. On the other side, there are people who apparently are intelligent, are good at interpreting evidence, but disagree with you regarding some proposition. Okay, I find this question hard. I was like, how am I supposed to respond to this? I don't know what you think, but personally, I feel like this is a hard topic. Okay, so this is part of the motivation for me to work on this project. So if we go back to like some more abstract discussion, we know that people need to be confident in what they believe to some extent. Okay, so I would say that most people believe that most of their beliefs are correct. Otherwise, you just cannot do anything. We need to make decisions every day, and we act upon our beliefs. So, without being fairly confident in our beliefs, we cannot take any action. Right? So, if you don't find this idea plausible, just imagine that there's a person who's full of self-doubt, who needs to make everyday, who need to make decisions. That'll be extremely tough, right? So people need to be confident, or at least fairly confident, in their beliefs. Okay. So namely, for most of us, we believe that most of our beliefs are correct. Okay? And because of that, we tend to see other people who have similar beliefs as reliable. The mechanism or the reasoning is simple. Because what I believe, so my beliefs are mostly correct. If somebody agreed with me regarding most of my beliefs, then that person must be correct as well. So that person must be reliable. Okay, so because we are confident in our beliefs, we tend to see others who have similar beliefs as reliable, so they are more likely to be correct. So it should be a natural thing for us to believe those who are similar to us. Fair enough. Okay, so Luke Skywalker once said to Darth Sidious that your overconfidence is your weakness. Okay. Well, Darth Sidious is apparently like an overconfident person. But the important or the interesting part is what Darth Sidious answered. He said, your faith in your friends is yours. Your faith in your friends is your weakness. Why do you say? Well, regarding this, I think Darth Sidious is like completely right. If you only believe in your friends, it's easy for you to be trapped in an epistemic bubble. So by an epistemic bubble, what is referred to is an epistemic network that has inadequate coverage through the process of exclusion by omission. So there are some like simple examples. One of the examples I like to use is about some rugby tournament. So does anyone here know which country won the Six Nations 2025? It's France. All right. I mean, it's fine that nobody knows. Okay. Because I also like Googled it to find out the answer. Six Nations is a rugby tournament that pretty much no one in Taiwan cares about. Okay. So this way, we can say that this piece of information is excluded from the community. So there are informations that we have no access to. So there's no intention of filtering these propositions or anything. It's just that these kind of information are omitted. Okay, so, but epistemic bubbles are fine. I mean, as long as you provide them with these information, people in the bubble will explode. People in the bubble can get to know new information. So now I'm telling you that which country won the Six Nations. You gradually know a little bit about rugby. An even worse case, like a much worse epistemic structure, epistemic network is epistemic echo chambers. So by echo chambers, what is meant is that there's a epistemic community, and members of this community only trust other members of this community, and they tend to see information outside of the community as false. So imagine that someone is in a cult or like in a special political party. They believe in what they believe their judgment is correct, they believe who they support is the right person. When there are information coming from outside the chamber that contradict with what they believe, they tend to say that these information are from unreliable sources and hence cannot be trusted. So when there are true information coming in to correct the beliefs of members in an epistemic echo chamber, they tend to take that as a piece of evidence that reinforces what they already believe. Namely, people outside the chamber are unreliable. Okay, so this is a much worse case. So if you trust only like-minded people, it's bad. Okay. All right. So you see that the conclusions to say that we need to have unlimited trust to people, right? Because if you want to avoid being trapped in an epistemic bubble or epistemic echo chamber, you need to trust people who are very, very different thing. Okay, that's ideally that's the way to get you out of this kind of toxic or problematic epistemic structures. But this is also wrong. Think about this. This is the memorial of Jewish people in Europe. There are Holocaust deniers. There are people who believe that Holocaust has never happened. Well, so this is like not a local example. So I've met people who tell me that there were only few hundred of people, or even fewer than 100 people who died in the February 28th incident. Well, it's actually my uncle. So he told me that, well, according to some historical texts, according to the historical evidence someone else discovered, there were only few people who got murdered within that incident. I was like, this is crazy. And so this might not be a good example, but I also have a friend who said that during the protests in Hong Kong several years ago, there were only like 50-ish people who got injured or killed. And I was like, that doesn't sound like accurate. That sounds like a very strange thing. All right, you don't want to trust these people. Or, I mean, if you say that their evidence is also evidence, this seems to be like a strange thing. You don't want to compromise with people and admit that maybe the Holocaust had never happened. Maybe the February 28th incident was not a huge thing. It is strange. There are also anti-vaxxers. Anti-vaxxers say that vaccination is correlated to autism, which, well, we probably all know is false. But they did make their claims without evidence. They say that there are scientific research, there are a lot of evidence showing the correlation between autism and vaccination. They have evidence. Some of them seem to be able to provide arguments. Do you want to agree with that? Do you want to agree that, yeah, well, maybe vaccination is not a good thing. Maybe vaccination is related to autism somehow. You probably don't want to do that, right? So the problem is, we just don't want to trust everyone. Okay, think about this. According to an unreliable survey, there are 4% of Americans who believe in lizard people theory. So 4% of Americans, well, so the number is like inaccurate because the research itself is not very reliable. But there are some people in the US who believe that the world is governed by lizard people. It's crazy. We don't want to trust that. We don't want to trust. I mean, when it comes to lizard people, I just don't want to trust these people. So we don't want to trust everyone. But on the other hand, we cannot only trust like-minded people. How are we going to choose who to trust? So this is the core question that I aim to explore. So what are the limits of trust? This seems to be an important thing, right? So I say, so now what I agree, or what I'm inclined to do is that I'm not going to only trust people who share similar beliefs with me. But I also don't want to compromise with people who have like drastically different views from mine. So what are the limits of trust? Before we answer this question, we need to answer how can we find the limits of trust? This is, as I stated, also an important question. So, I mean, you can of course make experiments, you can make philosophical arguments, but is there any way or systematic way for us to answer this question or to find out the answer? Okay, so what I suggest is to use models. Right, so we create a hypothetical abstract scenario and simulate how people exchange information within these models and see at the abstract level what will happen. Okay, that could be one way of exploring this question. Okay, so the model that I'm going to adopt is Kevin Zollman's network model. So he actually didn't invent the model himself. It was originally a model in economics. So he kind of modified the model to capture what he wants to capture. All right, so in this model, first of all, think of a single agent. So think of a single agent who's a scientist, or who's someone who aims to find out whether a proposition is true or not. Okay, so there's a proposition A is effective. Say A is a therapy for a disease. So the agent wants to find out whether this proposition is true. So by saying that this proposition is true, the opposite proposition will be another therapy B is effective, or no therapy. So it could be interpreted in both ways. But anyway, let's focus on this proposition A is effective. Right, so the scientist want to verify this claim. Right, so the scientist is randomly assigned with a credence in the proposition. Okay, so this part is related to what we're going to do later. And then if the assigned credence is above 0.5, the scientist believes that A is an effective therapy. So the scientist will perform A. Otherwise, the scientist will do nothing. All right, so if the scientist chooses to perform A, the scientist will do 100 trials. So make 100 experiments regarding the effectiveness of A. So after 100 trials, the agent collects some experimental results and update their credence accordingly using quantization, namely Bayes' rule. So think of a real-life scenario. Think of a doctor who treats 100 patients with A. So it could be like a simple therapy, it could be a kind of drug, it could be anything else like that. Okay, so the doctor treats 100 patients with A and check out the rate of recovered patients to see whether A is effective. All right, so it is assumed that the probability for the agent getting the right result is 0.501. So there's a slightly positive probability for the agent to collect true evidential results, experimental results. Okay, so this is set to 501 because originally what Zollman wants to capture is the spread of misinformation. So if it is set to 7 or it's set to 8, then information will be too correct, so we cannot know how misinformation is spread. All right, so the agents conduct only 100 trials, while the maximum is 0.001, which means that they get a large number of incorrect results. All right, so what I just described is a scenario involving only a single agent. Now, the single agent exchanged information with others. So what Zollman intends to find out is what is the ideal structure of a scientific community. So now, imagine that there are, say, 100 or 1,000 scientists who do the same thing as our agent does. So what is the ideal way for them to communicate, to exchange information, so that they can reach true consensus? They can form true consensus effectively. Okay. So after 100 trials, the agent updates their credence based on both their own evidence and the evidence their neighbors have collected. Okay. Their neighbors are those who are connected. So the agent directly sees the experimental results of their neighbors. All right, so how do they connect to their neighbors? This is the core question that Zollman wants to explore. Right? So should the community be highly connected or like minimally connected? So there are 3 different structures. The first one is cycle. So every single agent is connected to only 2 other agents within the community. So this is the least connected one. And also we have a wheel. So every agent, think about the structure as a wheel. Every agent is connected to 2 neighbors and a center. Okay, so you have a center of the wheel. And the last structure Zollman discussed is the complete structure in which every agent is connected to every other agent. Okay, so yeah, you can imagine, you can draw that down this way. This is the complete one. This is wheel. This is cycle. So when it comes to the connectedness of each, you see that this is lowest, this is the highest. Okay. So the intuitive idea is that this should be the best one, right? Because people exchange information frequently. Well, so I make experiments, you make experiments, I take your experimental results, and I got more informed. So this is supposed to be the best structure. This is supposed to be the worst one. But okay, so now what they do is this. they make experiments, they exchange information, namely the evidence they get, they update with beta school. And then they repeat this process. So if their credence is above 0.5, they make another round of experiment, and then exchange, update. Okay. So there are two terminate conditions. So first of all, if every agent's credence is above 0.9999, the simulation stops. Okay, because everyone get the right result. So they converge on the truth. If every agent's credence is below 0.5, then no one's going to perform A, so there's not going to be any new evidence coming in for the society. Alright, so the simulation also terminates. Alright, so Zollman's effect says that highly connected communities, namely the complete one, are less likely to converge on the truth. So he compared the probability of converging to the truth of 3 different structures and realized that because of the influence of misinformation, complete communities are less likely to converge on the truth. Right? But, well, so yeah, the reason is simple. Mistaken results spread faster in these communities. Okay, but to explore whether we should trust only like-minded ones, we need another model to do this. So we have the Hegselman-Krause model, which was invented around 20-ish years ago, right, by 2 philosophers of science. All right, so, well, this part, so u plus 1 is the time for the agent. So at time u plus 1, the agent i's credence is equal to everyone, every other person, every other agent in the bounded confidence interval. The sum of the credences divided by the number of these members. So suppose there are like 5 people in the community, and then you trust everyone. So you just take the sum of these and your own credence divided by 6. That would be your credence at the next time, at the next moment, right? So this is the Hegselman-Krause model, which is fairly simple, right? So consider the credences of those within the bounded confidence interval. Bounded confidence interval refers to the interval of the people you trust, okay? And there's a probabilistic version, which is a little bit slightly more complicated, but still follow the same basic idea. Okay, skip this part. So agents interact with others within their bounded confidence interval, BCI. This is the core part of this model. Agents interact with others whose credences are not too different from theirs. Alright, so what we want to know is how different is considered too different. How different is too different, so we don't want to compromise. We don't want to take their opinion seriously. Okay, so I modified the model. I modified Zollman's original model and say, so in this model, in my model, the epistemic structures are no longer fixed. So in Zollman's original simulation, there are like 3 different models, 3 different structures, right? Cycle, wheel, and complete. But here, what we do, or what my model does, is that we check whose credence falls within their PCI. So each agent establishes a new connection with those in the PCI, and then interact with them. So, and after each round of trials, the agent re-establishes connection with other agents, and then repeat the process. Okay, so now this is what an agent does. So assign with a random credence, conduct experiments, update their credence, and then check out who's within the BCI, and then exchange evidence with those agents within the BCI, and then back to 2. Okay, so the simulation now, the simulation is slightly modified now. Right. So the direct thing to do is to try out different functions. Right. So from point 1 to point 10. So here, epsilon refers to the error rate. So the blue one is the most unreliable group, while the purple one is the most reliable group. Right. So here, the value is the probability of converging to the truth. Okay, so if the threshold is 0.1, namely people only interact with other agents whose credence, whose difference, that has a credence that's not that's not overly different. Namely, the difference is below 0.1. This is the result. So they cannot. So the number on the x-axis are the size of the community. So here's the number of agents. So you can see that if the community is fairly close-minded, then this is the result again. They pretty much cannot form true consensus, right? And when we revise these threshold to 0.2, similar things happen, and then gradually it increases, right? So when the threshold is 0.7, there's a slight chance for these groups to form true consensus, right? But at this point, you might find this a little bit strange, because if you check the graph, if you check the figure, you might find that the blue one is supposed to be the unreliable group, but the blue community has a greater probability of forming true consensus, which is weird. Okay, so the same thing happens here, right? But if you think about it, it should be easy to imagine. So the two groups, so here, when the threshold is 0.9, you get the same result. So some agents get excluded faster. So imagine that. So imagine what agents with epsilon 0.1 does. So they collect information. They get the true belief. They get the true credence faster than other people in the same community. So there are some other agents that cannot interact with them anymore. So a single agent in these communities get the right result quickly, and then as a result, some were left out. Okay, so this is not like a very important thing though. When the threshold is 1, namely you have unlimited information exchange. We will do unlimited information exchange. It's likely for them to arrive at the same result, which is good. Okay. But so the interim conclusion we have here is that the more open-minded, the better. But as we can see, the result is more trivial. Well, the agents exchange evidence with others who are equally competent. So, of course, it's a good thing. You just want to collect as much information, as much evidence you want as possible. So it's no surprise that interacting with more agents leads to better outcomes. So back to the core question that I would like to explore: when should we be close-minded? Are we ever justified, or would it be ever legitimate for us to be close-minded? Right. So what I want to do is to separate agents into different subgroups with different epsilons. So some people in the community are smart, are better in interpreting evidence. Some others are less good in doing this. Right. So one group is more reliable, the other less so, but agents are unaware of which is which, like we are. Okay. So the agents still exchange. This is what I would like to explore. So now we separate the community into different subgroups. So when we have 10 reliable agents and 40 reliable ones, still the maximally tolerating is the best thing, is the best strategy. Right? This is not surprising because the number of unreliable agents is lower than reliable ones. So in this community, the majority of people are reliable. So if everyone exchanges information with each other, they reach true consensus easily. Right. So if we swap the numbers, we get 40 unreliable agents and 10 reliable ones. Still, you get the same result. That will have threshold 1.0 brings you with the better outcome. Okay. So if we try out smaller difference in epsilon, you get the same result. So now you have 5 reliable ones, 95 unreliable agents. Yeah, pretty much the same. And even if we add one more subgroup, you get the same result. Okay, so I would say that again. So this is like a further examination involving 5 different subgroups with different epsilon and with different sites. So epsilon ranges from 0.001, 0.05, 0.01, 0.05 to 0.1. Okay, and the size, the most reliable group has 25 agents, while the most reliable one has 5. You get pretty much the same result that you need to you're better off if you exchange information with everyone else. Okay, so still this is not very surprising, I would say. So with a higher threshold, agents are more likely to interact with other reliable agents. Okay, so there's one case that could be more interesting. So the whole world. So this is a poem written by Xu Yuan. Oh, I just realized that we're pretty close to Dragon Boat Festival. So the whole world is soiled and I alone am clean. All men are drunk and I alone am sober. It's an old saying. So if there's only one sane person, if there's only one brilliant guy in a community, is it good for that person to interact with everyone? Okay, so still you get the same result. Suppose we have 49 unreliable agents, namely the blue one, and we have a reliable one. Still, the probability of that person to arrive at a true result increases with pressure. Okay, so even in such a scenario, it'll be better to.
Yeah, can I just ask a quick question? So, how do you define the probability of convergence? Because within the experiment, there's supposed to be like a group of agents, and within that group, there are a subgroup of agents who trust each other and form epistemic bubble or epistemic chamber whatsoever. So the probability convergence is the probability of all agents to converge on the truth, or the probability of the subgroup, the mutually trusting group, to converge on the truth. The subgroup.
Yeah. So I think I ran like 10,000 trials for each figure. Some were less, I think. But yeah, you just count the number of like trials in which they arrive at a true consensus, and you count the number of trials that they arrive at a mistaken consensus. And this is the result again. Okay, so even if there's a single person, a single agent who's reliable within a huge group of unreliable ones, still it should be like maximally tolerated. Okay. But this is not what we normally do things. So given what I just described, in these scenarios, the agents directly see other people's evidence. So everyone makes experiments, and I get to see my neighbor's experimental results, and I update that. Well, if you think about the process, you're like, yeah, it should be natural that, well, you still want to collect as much information as you want. So it's no surprise that you get this kind of result. But in real life, or in some other scenarios, we don't really see other people's experimental results. What we get is other people's predictions. So other agents tell you what their predictions about this proposition are. So it's like, how to find out like the probability of the Democratic Party winning the next election in 3 or 4 years. They're probably saying, I think 70%, or I think 80%. They're not going to show you their evidence for that. So a more common scenario is one in which people exchange their credences, not experimental results. All right, so when it comes to this, normally what we do is to use averaging functions. So it's like, if you believe that, or if someone is like equally competent as I am, and then that person believes that the Democrats winning the next elections has, there's like a 80% chance that the Democrats win the next election. I have, say, like 40. So 0.8 plus 0.4 divided by 2, that's the usual way to do things. All right, so what we need to explore is the property of averaging functions. Here we use linear averaging. So why is it important? first of all, we use that to form consensus. So this is a common way for us to form consensus. Secondly, you can clarify key properties of these functions. So when you apply these functions, you know what are the potential problems, or what are the potential outcomes. All right, so we don't always have direct access to other people's experimental results. That's what I just said. All right, so change the function we use here in exchanging opinion. All right, so what's the point? To establish more describing how agents collect evidence, to clarify the properties of different pooling, namely averaging functions. So the framework could be further elaborated to capture more complicated real-life scenarios. So I further modify this model to use averaging functions to do this. So the agents now assigned with a random number, conduct experiments, update their credence, check whose credence falls within their BCI, and re-establish connections. And then this is new step. Take the average of all the agents within their BCI as the new evidence. Okay, so now we're not checking other people's experimental results, but we take the average of other people's credence. So this is a little bit closer to Hegselman-Krause's original idea. And then, well, if the process doesn't terminate, then we're back to 2, right? So this is the result you get when you apply geometric average. So there are people discussing the properties of geometric average. They try to say that, oh, this is a good way, but in this scenario, it's impossible for them to form a true consensus if they adopt geometric average. This is not very surprising because geometric average enhances polarization. So when if there are like 2 agents, one's credence is above 0.9, another is not, then it will be dragged to the side that's closer to the one that has higher credence. So yeah, it's not surprising. And for multiplicative average, yeah, this is another pooling function that has been widely discussed in recent years, and it has a property of synergy. So if there are like 2 values both below 0.5, the multiplicative average of the 2 numbers will be much lower than the linear average. So we can skip the 2 functions here. So because, well, first of all, they're more complicated. Nobody used that in real life. Could be used in some weird situations, but most people just don't use that. And also, it doesn't bring you with any probability of reaching true consensus. Well, brings you with little chance of reaching true consensus, but it's too little, so forget about that. So we should focus on linear averaging. That's the most common and maybe, perhaps, the most simple pooling function. And well, if this is the most common way people form consensus, then it could be helpful to clarify its properties. So this is the simulation result. So if we have 45 unreliable agents, and in the blue line you have 5 reliable ones, well, it's kind of weird, but this is what the model shows, that the more reliable group has a lower probability of reaching true consensus compared to the unreliable subgroup. But somehow still, raising the threshold is better, because still, if you adjust the threshold and make it gradually higher, you get better results, right? Up to this point, up to 0.9. Okay, so this is another strange part that needs to be explained. Okay, because well, somehow from here to here, the probability of forming true consensus drops. Right, so or change the size of the subgroup and change the parameters, you get the same result. You have 50 unreliable agents, the blue one, 10 reliable ones, and 5 very reliable ones. So epsilon ranges from 0.001, 0.05 to 0.1. You get pretty much the same result. So when the threshold is above 0.5, you get good results, right? And then gradually it gets better slightly, but still it drops after 0.9. Okay, this is somewhat strange. And another thing to notice is that the most reliable group, namely the green one, is not the one that performs the best. Okay, so the poorly performed one is the red group. This is also another slightly strange result. Okay, so now we have 20 each. We have 4 different subgroups, 20 members each, and when the threshold is about 0.5, the result gets much better. But still, we have this problem that you don't want to be maximally tolerating. Right? So you change the number, you get similar results here. Right? And also, now we have 5 subgroups, different size. You get this as well. And here, the effect gets more significant. So the difference between subgroups with threshold 0.9 and subgroups with threshold with 1.0 gets greater. This is still slightly strange. Okay, so I also try out different cases. So there are like only a few reliable ones with a huge number of unreliable ones. So 2 out of 100. This is what you get. So we can kind of try to find out the underlying rationale. It's like the unreliable ones gain benefit from the reliable ones. So they interact with the reliable ones. So the probability for them to reach true consensus gets greater. Okay. So, but some people might say that the unreliable group might not want to collect information from the reliable ones, like we've all seen. Even in such a case, we can consider only the reliable ones. If we don't compare the two, but focus on the blue line only, still, when the threshold gets greater, the probability of forming true consensus gets greater, okay? Which is still a positive thing. And yeah, here with like an even smaller group of reliable agents, so it's like 3 out of 200, you get similar results. Okay, so there's a strange discovery. Being slightly close-minded increases the probability of forming true consensus. Namely, you want to stop at 0.9, or yeah, in this case, 0.8 is better. And in this case, still like 0.9 should be the cutting point. Okay, so misinformation spread more quickly and effectively among maximally open-minded agents. That's the conjecture that we can see that we can derive from the model. Alright, another thing is that the least reliable groups are not necessarily the least likely to form a true consensus. They gain benefit from the reliable ones, as we saw. So, in all these cases, the most unreliable group collect information from other groups and then perform fairly well. Right? This is another intriguing, but I think interesting discovery. Okay, so yeah, the good news, perhaps, is that we're allowed to dismiss some extreme voices. If you strongly believe in some propositions, then you don't need to be maximally tolerating. You don't have to take the evidence or take the idea of those who are drastically different from you, but only condition that we use linear averaging to form consensus. Alright, so what needs to be done next is that, well, I would like to consider multiple propositions and to see the effective way for people to collect information and further clarify properties of these functions. So there might be other properties that remain to be explored, and also I want to apply them to some real scenarios to see if these scenarios fit what I described. Okay, so this is it. Thanks. Thank you for